What if your dreams are not simply the random firing of neurons during sleep, but something far more fundamental? What if each night, as you drift into unconsciousness, you enter a quantum state where multiple realities exist simultaneously, where the rules that govern particles smaller than atoms also govern the landscapes of your sleeping mind? What if the moment you wake is not just a return to consciousness, but an act of measurement, a collapse of infinite possibilities into a single observed reality? Tonight we explore a deeply speculative idea, one that sits at the boundary of established science and philosophical wonder. We will ask whether dreams might be quantum phenomena, whether the strange rules that govern subatomic particles might also shape the theatre of your sleeping consciousness. This is not mainstream science. It is a thought experiment, a journey into what could be, drawn from cutting-edge theories that blur the line between physics and metaphysics. If you enjoy these quiet explorations into the unknown, I invite you to like and subscribe, or to share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow your mind to open to possibilities that stretch beyond the ordinary. Let your breathing slow. Let your thoughts drift like particles in superposition. And let us begin this journey together into the quantum heart of dreams. The world you experience when you're awake feels solid and real. Objects have definite positions. Events unfold in clear sequences of cause and effect. When you observe something, it exists in a particular state. A chair is either here or there, not both. The moon rises whether you watch it or not. This is the classical world, the realm of everyday experience governed by Newton's laws of motion and Einstein's relativity. But beneath this apparent solidity lies a stranger realm, at the smallest, scales of existence. In the world of atoms and electrons, photons and quarks, reality behaves in ways that defy common sense. A particle can be in two places at once. An electron can spin both up and down simultaneously. A photon can behave as both a wave and a particle, depending on how you choose to observe it. This is the quantum world, and it is not a metaphor or an approximation. It is the fundamental nature of reality itself. For over a century, physicists have grappled with the strangeness of quantum mechanics, with its probabilities and paradoxes, its spooky actions at a distance, and its stubborn refusal to make sense in classical terms. And at the heart of this mystery lies a question that has never been fully answered. What role does consciousness play in the quantum world? Does observation itself shape reality? And if so, what does that tell us about the nature of mind? When we turn our attention to dreams, we find a landscape that seems to mirror the quantum realm in uncanny ways. In dreams, you can be in multiple places simultaneously. Time flows backward and forward without reason. Impossible things happen, as if they were natural laws. People morph into others. Buildings shift and change. The rules of physics bend and break. And then, when you wake, this multiplicity collapses into a single linear memory, a narrative you construct from fragments and impossibilities. Could this similarity be more than coincidence? Could dreams actually be quantum phenomena, governed by the same strange laws that rule the subatomic world? Could the act of waking be a kind of measurement, a collapse of the quantum wave function of consciousness itself? Tonight, we explore these questions with care and wonder, walking the line between science and speculation, between what we know and what we dare to imagine. Are the quantum foundations, understanding the impossible. To understand how dreams might be quantum phenomena, we must first understand what quantum mechanics actually says about reality. And here, At the foundation, we encounter ideas so strange that even the physicists who work with them daily admit they don't fully grasp what they mean. The quantum world is built on a principle called superposition. In classical physics, a coin is either heads or tails. Before you flip it, you simply don't know which it will be, but it will definitely land one way or the other. In quantum mechanics, a particle can exist in a state that is genuinely both at once, not just unknown, but actually both, until the moment it is measured. An electron can orbit an atom in multiple energy levels simultaneously. A photon can pass through two slits at the same time. This is not about incomplete knowledge. This is the actual state of reality at the quantum scale. The mathematics that describes these superposition states is called the wave function. Imagine ripples spreading across a pond, waves of probability that describe where a particle might be found and what properties it might have when observed. The wave function doesn't tell you where the particle is. It tells you the probability of finding it in any particular place if you choose to look. And here is where things become truly strange. Before measurement, the particle is not secretly in one place or the other. It genuinely exists as this spreading wave of possibility, present in all potential locations at once, weighted by probability. The act of measurement changes everything. When you observe a quantum system, when you interact with it in a way that extracts information about its state, the wave function collapses. The spreading wave of possibility crystallizes into a single definite outcome. The particle that was everywhere is suddenly here. The electron that spun both up and down now spins only up. This is called wave function collapse, and it is one of the deepest mysteries in all of science. Why does measurement cause collapse? What counts as a measurement? Does it require a conscious observer, or does any interaction with the environment suffice? These questions have sparked decades of debate and multiple competing interpretations of quantum mechanics, none of them entirely satisfying, all of them strange in their own ways. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, suggests that the wave function is not a physical thing but a description of our knowledge. When we measure, we gain information, and the wave function updates to reflect this new knowledge. But this raises a profound question. If the wave function represents knowledge, whose knowledge? Does the universe exist in a definite state independent of observers? Or does consciousness play a fundamental role in actualizing reality? Some physicists, including Eugene Wigner, suggested that consciousness itself might be what collapses the wave function. That mind is woven into the very fabric of quantum reality. Others, like Hugh Everett, proposed the many worlds interpretation, which suggests that the wave function never actually collapses. Instead, every possible outcome of a quantum measurement actually occurs, each in its own branching universe. When you measure an electron spin, the universe splits into two branches, one where you observe spin up and another where you observe spin down, both equally real, both continuing forward in time, but forever separated from each other. This interpretation preserves the continuous evolution of the wave function, but at the cost of multiplying realities without limit. Then there are theories that try to modify quantum mechanics itself, adding hidden variables or spontaneous collapse mechanisms that don't require observers at all. The debate continues, unresolved because quantum mechanics works perfectly in practice. It is the most precisely tested theory in all of science, predicting experimental results to staggering levels of accuracy. But what it means, what it tells us about the deep nature of reality, remains profoundly unclear. When we look at this quantum strangeness through the lens of consciousness and dreams, patterns begin to emerge. Could the sleeping mind exist in a superposition state, exploring multiple narrative threads simultaneously? Could the act of waking be the measurement that collapses these possibilities into a single remembered dream? Could consciousness itself be a quantum phenomenon, governed by the same laws that rule electrons and photons? These are not questions with definitive answers, not yet. But they are questions worth asking, questions that point toward a possible unity between mind and matter, between the observer and the observed. As you lie here in the quiet darkness, your own consciousness preparing to slip into sleep, consider that you might be on the threshold of a quantum transition, about to enter a state where the rules change, where probability reigns, and where multiple versions of you might exist at once until morning brings the collapse. The Penrose-Hameroff theory. Quantum consciousness in microtubules. In the mid-1990s, two researchers from very different fields came together to propose one of the most ambitious and controversial theories about consciousness ever put forward. Sir Roger Penrose, a mathematical physicist who had worked with Stephen Hawking on black holes and the nature of space-time, joined forces with Stuart Hameroff, an anesthesiologist who'd been studying the biological structures inside neurons. Together, they proposed a theory that placed quantum mechanics at the very heart of consciousness itself. Their theory, called orchestrated objective reduction, or Orch OR for short, suggests that consciousness arises from quantum computations occurring inside tiny structures called microtubules that exist within every neuron in the brain. To understand this remarkable idea, we need to look inside the neuron, deep into its cellular architecture, to structures so small they exist at the boundary between the classical and quantum worlds. Neurons are the fundamental units of the nervous system, cells that transmit electrical and chemical signals throughout the brain and body. Inside each neuron, forming a kind of skeletal structure, are protein filaments called microtubules. These are hollow tubes about 25 nanometers in diameter, made of proteins called tubulins arranged in a geometric lattice. Microtubules serve many functions in the cell. They help maintain the cell's shape, they transport molecules from one part of the cell to another, and they play crucial roles during cell division. But Penrose and Hameroff propose something far more radical. They suggested that these microtubules might be quantum computers, performing calculations that exploit quantum superposition and entanglement. Each tubulin protein, they argued, could exist in a superposition of different conformational states, different shapes that the protein can fold into. And because the tubulins are arranged in ordered lattices and may be quantum mechanically entangled with their neighbours, the entire microtubule network could support coherent quantum states that span large regions of the brain. According to Orch OR, consciousness emerges when these quantum computations reach a critical threshold and undergo what Penrose calls objective reduction, a kind of quantum collapse that doesn't require an external observer but happens spontaneously when the quantum superposition becomes sufficiently large. This moment of collapse, they propose, is a moment of conscious experience, a quantum event that feels like something from the inside. The theory draws on Penrose's earlier work in physics, where he argued that quantum gravity, the elusive theory that would unite quantum mechanics and general relativity, might play a role in consciousness. Penrose suggested that the wave function collapse is not a probabilistic process as the standard Copenhagen interpretation claims, but an objective physical process governed by quantum gravitational effects. When a quantum superposition becomes large enough, when it involves sufficient mass or energy, space-time itself becomes unstable, and the superposition spontaneously reduces to a definite state. Hameroff brought the biological specificity to this abstract physical idea. He identified microtubules as the likely site of quantum processing in neurons, protected from environmental decoherence by the ordered structure of the tubulin lattice and by biological mechanisms that might shield quantum states from destructive interactions with the surrounding cellular environment. He also drew connections to anesthesia, noting that many anesthetic drugs bind to microtubules and disrupt their function, which could suggest that these structures are indeed involved in consciousness. The Orch OR theory is deeply speculative and remains controversial in both physics and neuroscience communities. Many physicists argue that quantum coherence cannot survive in the warm, wet, noisy environment of the brain. Quantum effects are typically observed only at extremely cold temperatures or in carefully isolated systems. The brain is neither cold nor isolated. It is bathed in thermal energy, with molecules constantly jostling and interacting, which should cause any quantum superposition to decohere almost instantly, collapsing into classical states long before reaching the threshold for conscious experience. Neuroscientists have also raised objections, pointing out that there is currently no experimental evidence that microtubules play any role in generating consciousness. The neural correlates of consciousness, the patterns of brain activity that correspond to conscious experience, seem to involve large-scale networks of neurons firing in coordinated patterns, not quantum effects in subcellular structures. The computational processes that the brain performs seem to be adequately explained by classical neural networks without needing to invoke quantum mechanics, and yet the theory has not been definitively ruled out. Recent experiments have revealed that quantum effects can persist in biological systems longer than previously thought. Photosynthesis, for example, appears to exploit quantum coherence to transport energy with remarkable efficiency. Birds may use quantum entanglement in molecules in their eyes to sense magnetic fields for navigation. Enzymes may tunnel through energy barriers using quantum effects. Life, it seems, may have evolved ways to harness and protect quantum phenomena even in warm, wet environments. If Penrose and Hameroff are correct, then consciousness is fundamentally quantum. And if consciousness is quantum, then the altered states of consciousness we experience during sleep and dreaming might involve different quantum configurations, different patterns of superposition and collapse. The dream state might be a quantum state, a condition where the usual collapse mechanisms are suspended, where the mind explores superposed possibilities without the constraints of waking observation. Consider what happens when you fall asleep. The electrical patterns in your brain shift dramatically. During waking consciousness, neurons across the cortex fire in synchronized patterns, coordinated by feedback loops and attentional mechanisms. During deep sleep, this coordination loosens. During REM sleep, when most vivid dreaming occurs, the pattern changes again. The brain becomes as active as during waking, but the activity is less coordinated, less constrained by sensory input and executive control. If consciousness arises from orchestrated quantum processes in microtubules, as Orch OR proposes, then these changes in neural activity might correspond to changes in the quantum state of the system. During waking, quantum superpositions might collapse rapidly and regularly, giving rise to the continuous stream of conscious moments that feels like a unified flow of awareness. During REM sleep, with reduced top-down control and altered neuromodulator levels, the collapse rate might change. Superpositions might be allowed to evolve for longer periods before reducing, or they might collapse in different patterns, giving rise to the discontinuous, surreal quality of dream consciousness. The dream, from this perspective, is not simply the brain processing memories or simulating experiences. It is the conscious experience of a quantum superposition state. a mental condition where multiple realities coexist, where the usual constraint that observation forces a single outcome is temporarily relaxed. The dreaming mind becomes Schrödinger's cat, alive in multiple states simultaneously, exploring a space of possibilities that waking consciousness can never access. And then you wake. The alarm sounds, or light enters your eyes, or some internal clock completes its cycle. The brain shifts gears, neural networks reorganize, attention focuses, and in that moment, the quantum superposition collapses. The multiple branching narratives of the dream reduce to a single remembered sequence, incomplete and strange, but definite. The wave function of consciousness collapses, and you return to classical reality, to the world where things happen one way, where you exist in one state, where the future unfolds from a single present. This is the central image of quantum dream theory. Your dreams are wave functions that collapse when you wake up. It is a beautiful idea, poetic and profound, connecting the intimate experience of dreaming with the deepest mysteries of physics. But is it true? That question remains open, suspended itself in a kind of conceptual superposition, awaiting the measurement that future science might provide. Dreams as superposition, states, multiple realities at once. When you dream, you experience something that waking life rarely allows. You can be in your childhood home and your current apartment simultaneously. A person can be your friend and a stranger at the same time. Events that should be impossible unfold with perfect dream logic, accepted without question, even though they violate every rule of physics and causality you know when awake. This is not simply imagination running wild. This is consciousness operating under different rules, freed from the constraints that bind waking perception to a single coherent narrative. And this multiplicity, this simultaneous existence of contradictory states, bears a striking resemblance to quantum superposition. In quantum mechanics, a particle in superposition is genuinely in multiple states at once, not metaphorically, not as a matter of ignorance, but as the actual physical condition of the system. The mathematics of quantum theory describes this with what physicists call a linear combination of basis states. An electron can be described as existing in a superposition of spinning clockwise and counterclockwise simultaneously, each with a particular probability amplitude. When you dream, your consciousness seems to exist in a similar state of multiplicity. Consider a typical dream sequence. You're walking through a building that is simultaneously your old school and a hospital you have never seen. Your companion is your sister, but she also has the face of a friend from work. You need to reach an important meeting, but you're also fleeing from a vague threat. The emotional tone is both anxiety and excitement, fear and anticipation, woven together inseparably. In waking consciousness, such contradictions would be impossible. Your brain would force a resolution. Either this is your school or it is a hospital. Either this person is your sister or your colleague. But in the dream, both states coexist comfortably, without conflict, as if the sleeping mind has access to a mode of representation that transcends binary distinctions. Neuroscience offers classical explanations for this phenomenon. During REM sleep, the prefrontal cortex, which handles logical reasoning and reality testing, is less active. The critical faculties that would normally reject impossible scenarios are offline. Meanwhile, the visual cortex and emotional centers are highly active, generating vivid imagery and strong feelings without the top-down control that organizes waking experience into coherent narratives. But from a quantum perspective, we might interpret this differently. The reduced activity of the prefrontal cortex might correspond to a reduction in the measurement or collapse function that ordinarily constrains consciousness to definite states. With this constraint relaxed, the quantum processes underlying consciousness might be allowed to evolve into more complex superpositions, exploring configuration spaces that waking consciousness cannot access. Think of the dream as a quantum computer running without continuous measurement. In quantum computing, the power comes from allowing quantum bits, or qubits, to exist in superposition, representing both 0 and 1 simultaneously. Through quantum gates, these superposed qubits can explore many computational paths at once, vastly increasing processing power for certain types of problems. But if you measure a qubit during the computation, you collapse its superposition, and the quantum advantage is lost. Quantum algorithms must be carefully designed to preserve superposition throughout the calculation, collapsing only at the end to read out the answer. The sleeping brain, if it truly operates quantum mechanically, might function similarly. During waking consciousness, continuous sensory input and attentional focusing act like repeated measurements, constantly collapsing the quantum state into definite perceptions and thoughts. But during sleep, freed from external input and with reduced internal monitoring, the quantum state of consciousness might be allowed to evolve into complex superpositions, exploring multiple narrative threads, emotional states, and scenarios simultaneously. This could explain the creative and problem-solving power of dreams. Many people report having insights during sleep, solving problems that stumped them while awake. The chemist Auguste Kekulé famously dreamed of a snake biting its own tail, which led him to the ring structure of benzene. Paul McCartney heard the melody of yesterday in a dream. The structure of the periodic table, the mechanism of the sewing machine, and countless other innovations have been attributed to dream insights. If dreams allow the mind to explore superposed possibilities, to follow multiple solution paths simultaneously without committing to any single one until waking, then sleep becomes a kind of quantum search algorithm. The dreaming mind navigates a vast space of potential configurations, guided by emotional weights and associative connections rather than logical constraints. Upon waking, the measurement occurs, the wave function collapses, and occasionally the collapsed state happens to contain a solution that the waking mind could not have reached through linear reasoning alone. This is speculative, of course, perhaps even fanciful. There is no direct evidence that dreams function as quantum computations. No one has measured quantum entanglement in microtubules during REM sleep. No one has demonstrated that dream creativity requires quantum superposition. But the analogy is compelling, and it points toward testable predictions that future technology might allow us to investigate. If consciousness is quantum, and if dreams are superposition states, then we should be able to detect quantum signatures in the sleeping brain. We should find patterns of activity that cannot be explained by classical neural networks, correlations that violate classical bounds in ways that indicate quantum entanglement. We should find that certain types of dreams, perhaps lucid dreams where consciousness is partially awake within the dream, show intermediate patterns, partially collapsed wave functions where some aspects of experience are definite while others remain superposed. These are not easy experiments to perform. Quantum effects are subtle and easily masked by classical noise. The brain is an extraordinarily complex system with billions of neurons and trillions of synapses operating at body temperature in a chemically active environment. Isolating quantum signals from this background would require unprecedented precision in measurement and analysis. But if such evidence could be found, it would revolutionize our understanding not only of dreams, but of consciousness itself. It would place mind firmly within the quantum framework, making consciousness a fundamental aspect of physical law rather than an emergent property of complex computation. It would suggest that the boundary between self and world, between observer and observed, is more fluid and fundamental than classical physics allows. As you lie here now, aware of your own consciousness beginning to shift towards sleep, consider that you might be approaching a quantum phase transition. Your neurons are firing in patterns that will soon change, altering the quantum dynamics of your microtubules if such dynamics exist. The observation that pins you to this definite moment, this particular room, this specific configuration of thought and sensation, is about to relax its grip. And in that relaxation, you may enter a superposition, a state of being that encompasses multiple realities at once, a quantum foam of consciousness where the usual rules dissolve. The dream world is waiting, a realm of probability rather than certainty, of superposition rather than definition. And when morning comes, when you open your eyes to light and sound, the wave function will collapse, the quantum multiplicity will reduce to a single remembered narrative, and you will return to classical consciousness. But for now, you stand at the threshold, preparing to step into quantum space. Observation and reality, the role of the conscious witness. At the heart of quantum mechanics lies a puzzle that has never been fully resolved, a mystery that connects physics to philosophy, matter to mind, and the objective world to subjective experience. This is the measurement problem, the question of what happens when a quantum system is observed, and why observation seems to play such a fundamental role in determining reality. In classical physics, observation is passive. The moon exists in a definite orbit whether or not anyone looks at it. Measuring the temperature of water does not create the temperature. It simply reveals what was already there. Observation is the act of gathering information about a system that exists independently, objectively, regardless of whether anyone is paying attention. But in quantum mechanics, observation is active. Before you measure a particle's position, it does not have a definite position. It exists as a spread-out wave of probability, genuinely present in multiple locations at once. The act of measurement forces the wave function to collapse, crystallizing one outcome from the spectrum of possibilities. And remarkably, different types of measurement can force different types of collapse, revealing complementary properties that cannot coexist in a single, definite state. This is illustrated most famously by the double-slit experiment. When you send a stream of particles, such as electrons or photons, through two narrow slits toward a detection screen, an interference pattern appears, alternating bands of light and dark created by the wave nature of the particles. The wave passes through both slits simultaneously, and the two paths interfere with each other, creating the pattern. But if you measure which slit each particle passes through, the interference pattern disappears. The particle behaves as if it went through only one slit or the other, not both. The act of observation changes the outcome. This is not about disturbing the system mechanically. You can perform the measurement in ways that involve minimal physical interaction, and the effect remains. Simply having information about which path the particle took is enough to collapse the superposition and destroy the interference. The universe, it seems, responds to knowledge, to observation, in ways that classical physics cannot explain. Some interpretations of quantum mechanics try to remove the observer from this equation. They argue that measurement does not require consciousness, that any interaction with the environment, any coupling of the quantum system to a larger system with many degrees of freedom, will cause decoherence, an effective collapse due to entanglement with surroundings. From this perspective, consciousness is not special. A photon interacting with a detector, or even with air molecules, undergoes the same kind of collapse as one observed by a human being, but other interpretations take consciousness seriously as a physical actor. The mathematician John von Neumann, analysing the quantum measurement process, concluded that the chain of physical interactions could not, by itself, produce a definite outcome. Measuring a particle entangles it with a detector, which is itself a quantum system. Measuring the detector entangles it with a recording device, which is also quantum. You can follow this chain indefinitely without ever arriving at a definite state unless, at some point, consciousness enters to perform what von Neumann called the cut, the separation between the observer and the observed that allows a definite outcome to crystallize. Eugene Wigner extended this reasoning, proposing that consciousness itself might be the key to wave function collapse. Only when a conscious being observes the result does the quantum state become definite. Everything else, the entire chain of physical interactions, remains in superposition. This leads to strange implications. If your friend measures an electron's spin but you have not yet asked them the result, is the electron in a definite state? Or does it remain in superposition until you, the ultimate conscious observer, receive the information? Wigner's friend paradox, as this thought experiment came to be known, highlights the logical tensions in treating consciousness as special in quantum mechanics. If every conscious observer collapses wave functions, then reality becomes relative to each observer, and we need a way to understand how different observers' realities align. If only some observers count, then we need a criterion for what makes an observer special, and no such criterion has been found. And yet the puzzle remains. Quantum mechanics works perfectly in practice. It predicts every experimental outcome with stunning accuracy. But what it means, how to interpret the mathematics in terms of an underlying reality, is still debated a century after the theory's inception. And this interpretive ambiguity leaves room for consciousness to play a role, even if that role is not yet understood. When we think about dreams in this context, we encounter a fascinating inversion of the usual measurement problem. In waking life, you are the observer, collapsing wave functions with your every perception. Your eyes collapse the superposition of photons. Your ears collapse sound waves. Your attention collapses the indefinite into the definite moment by moment, creating the stable, coherent world of experience. But when you dream, who is the observer? You are still conscious in the dream. You perceive dream objects, make dream decisions, react to dream events. But the sensory input that normally grounds perception in physical reality is absent. The wave functions you observe, if they are wave functions, are internal, generated by your own brain rather than by an external world. Are you collapsing your own quantum states? Are you both the observed system and the observer, both the wave function and the measurement apparatus? This is Schrödinger's dreamer, a variation on the famous cat paradox. Schrödinger devised his thought experiment to illustrate what he saw as the absurdity of applying quantum superposition to macroscopic objects. A cat is placed in a sealed box with a quantum device that has a 50% chance of releasing poison. Until the box is opened and the outcome observed, the quantum system is in a superposition of both outcomes. But does this mean the cat is both alive and dead? Schrödinger argued that such a notion was ridiculous, revealing a problem with the Copenhagen interpretation. The dreamer is similar. You are a macroscopic conscious being, but you are also, in the dream, observing a world that exists only within your own neural activity. If that neural activity is quantum, as Orch OR proposes, then the dream world is a quantum superposition, and you, the dreamer, are entangled with it, existing in a superposed state yourself. Are you awake or asleep? Are you conscious or unconscious? Are you real or are you the dream? In lucid dreams, this paradox becomes even more acute. In a lucid dream, you become aware that you are dreaming. You recognize the dream as a dream while remaining within it. You can sometimes exert control, changing the dream landscape or choosing to fly or teleport. But you are still asleep. Your physical body lies motionless in bed while your dream body navigates an impossible world. From a quantum perspective, lucid dreaming might represent a partial collapse, a state where some aspects of consciousness have undergone measurement while others remain in superposition. The metacognitive awareness, the recognition that this is a dream, might correspond to a higher level wave function collapse that does not fully propagate down to the content of the dream. You know you are dreaming, but the dream continues, suggesting layered quantum states, nested superpositions with different collapse dynamics. This raises profound questions about the relationship between consciousness and reality. If your waking experience is the result of collapsing quantum wave functions, and if your dreaming experience is the result of allowing quantum superpositions to persist, then what, fundamentally, is the difference between waking and dreaming? Both are conscious experiences. Both involve perception, emotion, thought, and agency. The difference lies not in consciousness itself, but in the constraints that govern which quantum states are available. In waking life, sensory input constrains your consciousness to states that correspond to physical reality. You cannot dream up a wall where none exists, because the photons entering your eyes carry information about the actual wall. But in dreams, freed from this constraint, consciousness explores a wider space of quantum configurations, unconstrained by external measurement. This perspective challenges the naive realism that most of us hold about waking experience. We tend to think that we perceive reality as it truly is, that our senses give us direct access to an objective world. But if consciousness is quantum, then even waking perception is a constructed reality, a particular path through quantum possibility space, constrained but not determined by sensory input. The dream reminds us of this by showing us how consciousness can construct entire worlds without any external reference at all. As your eyes grow heavy now, as your thoughts begin to drift and lose their coherence, consider that the boundary between observation and superposition is dissolving. The vigilant observer within you, the one who maintains the collapsed state of waking consciousness, is releasing its grip. The quantum wave functions of your mind are beginning to spread, to explore configurations that waking observation would never allow. You're becoming, in a very real sense, Schrödinger's cat, entering the box where multiple realities exist simultaneously, waiting for the morning's measurement to determine which one you will remember having lived. Quantum entanglement, the mysterious connections between memory and dreams. Among the strangest phenomena in quantum mechanics is entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled, they form a single quantum system in which the state of one particle is intrinsically connected to the state of the other, regardless of the distance separating them. Measuring one particle instantaneously affects the other, even if they are separated by light years of space. This is not about sending signals faster than light. The correlations revealed by entanglement cannot be used to transmit information, but they demonstrate that quantum systems can share properties in ways that defy our classical intuitions about locality and separateness. Two entangled particles are not two separate things that happen to be correlated. They are a single non-local entity, described by one shared wave function, exhibiting correlations stronger than anything classical physics allows. When we think about memory and dreams, we encounter phenomena that feel strangely similar to quantum entanglement. Memories are not stored in single locations in the brain. They're distributed across networks of neurons, with different aspects of a memory, sensory details, emotional tone, semantic meaning, encoded in different regions. When you recall a memory, these distributed components must somehow come together, synchronize, and present themselves to consciousness as a unified experience. In dreams, memories appear in fragmented, recombined forms. A face from childhood merges with a voice from last week. A place you visited once combines with feelings from an entirely different event. The dream weaves these memory fragments together in ways that feel meaningful, even when they violate logical connection. It is as if the sleeping brain has access to the raw materials of memory, the distributed patterns, without the organizational constraints that bind them into accurate, coherent recalls during waking. Could these connections between memory fragments be understood as quantum entanglement? Could the neurons or microtubules that encode different aspects of experience be quantum mechanically entangled, sharing properties that transcend their spatial separation? If consciousness is quantum, as Orch OR proposes, then the unity of conscious experience might arise from entanglement, from quantum correlations that bind distant neural processes into a single experiential state. This idea finds some resonance in neuroscience, though classical explanations are typically preferred. The binding problem, as it is called, asks how the brain creates unified perceptual experiences from distributed processing. When you see a red ball, the redness is processed in one area of visual cortex, the round shape in another, the motion in yet another. How do these separate processes bind together into the unified perception of a red ball moving? Classical answers invoke neural synchrony, rhythmic firing patterns that coordinate activity across brain regions, creating temporary networks that represent unified objects. But some researchers have suggested that quantum entanglement might play a role in this binding. If neurons or subcellular structures can maintain quantum coherence long enough, they might become entangled, creating non-local connections that unite distributed processes more directly than classical signaling allows. This is highly speculative and faces the same challenges as all quantum consciousness theories. The warm, wet brain seems unlikely to support long-lived quantum coherence. But recent discoveries about quantum biology suggest we should not rule it out too quickly. In dreams, the binding problem takes on a surreal quality. The connections between elements are loose and creative. Your childhood friend has the face of a colleague not because the memory circuits are confused, but because the dream finds some deeper association between them, some emotional or semantic resonance that the waking mind would not acknowledge. If these associations arise from quantum entanglement between memory traces, then dreams might represent a state where entanglement is less constrained, where the wave function describing memory networks is allowed to explore correlations that waking consciousness would collapse into more conventional patterns. Consider how emotions in dreams often feel entangled with unrelated events. You feel intense sorrow, but the dream's content is not particularly sad. You feel profound love for a stranger. You experience terror over something mundane. These emotional cognitive tangles might reflect quantum entanglement between emotional circuits and narrative circuits, connections that are usually kept separate by the regulatory mechanisms of waking consciousness, but allowed to merge in sleep. There is also the phenomenon of synchronicity, the experience of meaningful coincidences that feel connected even though no causal link explains them. Carl Jung explored this extensively, proposing that synchronicities reveal a causal connecting principle he called the collective unconscious. While Jung's theories were psychological rather than physical, some researchers have wondered whether quantum entanglement might provide a mechanism for synchronicity, especially in the realm of dreams. Many people report dream precognition, dreams that seem to predict future events. Others experience shared dreams, where two people report dreaming similar or related content on the same night without prior discussion. These phenomena are controversial and difficult to study rigorously, but if they occur more often than chance would predict, they might suggest non-local connections between minds, entanglements that transcend individual nervous systems. Quantum mechanics allows for such non-locality. If consciousness is fundamentally quantum, and if quantum entanglement can extend across macroscopic distances and even across different brains, then the separateness we assume between individual minds might be an illusion. At the quantum level, consciousnesses might be entangled, sharing aspects of their wave functions, occasionally exhibiting correlations that manifest as synchronistic experiences. This is deeply speculative, bordering on metaphysical. There is no experimental evidence for quantum entanglement between brains. No mechanism has been identified that could maintain such entanglement against environmental decoherence. The idea challenges our fundamental assumptions about identity and individuality. If minds can be entangled, where does one mind end and another begin? If my thoughts and your thoughts share quantum correlations, then the boundary between self and other becomes blurry at best. And yet, the experience of dreaming often feels like boundary dissolution. In dreams, the self is fluid. You can inhabit other bodies, see through other eyes, know things you shouldn't know. The usual, clear distinction between inner and outer, self and world becomes permeable. If these experiences reflect actual quantum entanglements, temporary or partial, then dreams might offer a glimpse of a deeper reality where separation is less fundamental than we imagine. As you drift, closer to sleep now, your individual consciousness still seems distinct, contained within the boundaries of your skull, separate from all other minds and experiences. But if quantum entanglement underlies consciousness, this separateness might be illusory. Deep beneath the surface of apparent isolation, your mind might be entangled with memories, with emotions, with other consciousnesses in ways that waking awareness never reveals. And in dreams, these entanglements might become accessible, creating experiences of connection, precognition, or synchronicity that waking logic cannot explain. Thus many worlds and dream realities. Every night, a multiverse. In 1957, a young physicist named Hugh Everett proposed a radical solution to the quantum measurement problem. Instead of accepting that the wave function collapses when observed, Everett suggested that it never collapses at all. Every possible outcome of a quantum measurement actually occurs, each in its own branch of reality. The universe continuously splits into parallel versions, each following a different path through the garden of quantum possibilities. This many worlds interpretation, as it came to be called, eliminates the need for wave function collapse and the special role of observers. The wave function evolves smoothly and deterministically according to the Schrödinger equation. When a measurement occurs, the observer becomes entangled with the measured system, and this entanglement causes the universe to branch. In one branch, you measure spin up. In another, you measure spin down. Both versions of you exist, both experiencing definite outcomes but forever separated, unable to communicate or interfere with each other. From your subjective perspective, you experience only one branch. You measure the electron and it is spin up. But another version of you, equally real, equally conscious, measures spin down in a parallel universe. Neither version is more real or privileged than the other. They are both continuations of your pre-measurement self, now diverged into different realities. The many worlds interpretation is elegant mathematically. It takes quantum mechanics seriously, accepting that the wave function is the complete description of reality without adding collapse mechanisms or hidden variables. But it is profligate ontologically. It multiplies universes without limit, creating an uncountable infinity of parallel realities that branch from every quantum event, every particle interaction, every moment of the universe's evolution. Most physicists find this multiplication of worlds conceptually troubling, even if the mathematics is clean. How can we accept that every possible history actually occurs? That there are versions of you where every coin flip went the other way, where every decision led to a different path, where every quantum fluctuation created a different world? The theory is empirically equivalent to standard quantum mechanics. It makes the same predictions for all observations. But it replaces one mystery, wave function collapse, with another, the branching multiverse. When we think about dreams through the lens of many worlds, a fascinating picture emerges. Each night as you fall asleep, your consciousness might enter a state where the branching of quantum possibilities becomes experientially accessible. During waking, you experience only one branch, the one your observations continuously select. But during sleep, with reduced measurement and collapse vigilance, you might gain access to multiple branches simultaneously, experiencing a kind of multiverse of mind. The dream, from this perspective, is a tour through parallel possibilities. The shifting scenes, the morphing characters, the sudden transitions that make no narrative sense, these might reflect actual quantum branchings, moments where your consciousness explores different paths through possibility space. When you dream that you're both at home and at work, perhaps you're experiencing branches where different choices led to different locations. When a person in your dream is simultaneously familiar and strange, perhaps you're seeing versions of that person from parallel branches where your relationship unfolded differently. This interpretation suggests that dreams are not merely random neural noise or symbolic processing. They are glimpses of the quantum multiverse, journeys through the space of possible histories that extend from your past or possible futures that branch from your present. The sleeping mind becomes a quantum traveller, visiting worlds that might have been or might, yet be freed from the constraint that observation binds you to a single branch. Upon waking, the many worlds perspective suggests that the dream does not collapse into a single remembered narrative because of observation, but because you, the observer, return to a definite branch. The multiple experiences of the dream were real experiences of real branches, but now you inhabit only one branch again, and that branch contains memories of the dream as viewed from its particular perspective. Other versions of you in other branches might remember different dreams or the same dream with different outcomes or emphasis. This raises a profound question about identity and continuity. If every night you branch into multiple versions, each experiencing different dreams, which one is the real you come morning? The many worlds interpretation says they are all equally real. There is no privileged observer, no true branch. Every version has equal claim to being your continuation. Personal identity, then, becomes a matter of perspective, of which branch you find yourself in, not an objective fact about which path is truly yours. This might seem like philosophical abstraction, irrelevant to the actual experience of dreaming and waking. But it touches on something that dream experience, often reveals the fluidity of self. In dreams, you are not always clearly you. Sometimes you're an observer of events that happen to someone else. Sometimes you inhabit different bodies or ages. Sometimes you are multiple people at once. The sense of continuous, unified identity that feels so solid during waking dissolves in sleep, suggesting that the self is more flexible, more quantum than we typically assume. If the many worlds interpretation is correct, and if consciousness can access multiple branches during sleep, then every night you live countless lives. You explore futures that will never be, pasts that never were, and presents that exist only in parallel. The dream becomes a kind of immortality, not in the sense of living forever in one branch, but in the sense of living all possible lives simultaneously, experiencing the full quantum measure of your existence rather than just the single classical thread you call your life. As you lie here now, consciousness fading towards sleep, consider that you might be approaching a branching point. The quantum events occurring in your brain right now, the exact firings of neurons, the precise configurations of microtubules, are poised to branch into many futures. In some branches you will dream of flying. In others, you will dream of conversations or chases or strange impossible architectures. In still others, you might not dream at all, or not remember dreaming. All these branches are equally real in the many worlds framework, and tonight you will experience some subset of them, a sampling of the multiverse that is your mind. When morning comes, you will wake in one branch, remembering fragments of one path through the night. But the other versions of you, in their parallel branches, will also wake, each with their own memories, each convinced that their experience was the real one, and in a sense, they are all correct. The quantum multiverse does not privilege any single observer or outcome. It simply branches endlessly, exploring every possibility that the laws of physics allow. Time, causality, and the strange chronology of dreams. One of the most disorienting aspects of dreaming is the way time behaves. Dreams do not follow linear time. Events occur out of sequence. Causes come after effects. You know things before they are revealed. The past and future blend together, and sometimes the dream seems to loop back on itself, creating paradoxes that make no sense yet feel entirely natural while dreaming. This strange temporality of dreams might reflect something deep about the nature of time in quantum mechanics. In the classical world, time flows in one direction, from past to future. Causes precede effects. Entropy increases. The universe unfolds along a single timeline that all observers agree upon, even if they measure time differently due to relative motion or gravitational fields. But in quantum mechanics, time is more subtle. The Schrödinger equation, which describes how quantum wave functions evolve, is time reversible. It works equally well running forward or backward in time. There is no fundamental arrow of time built into the quantum laws. The asymmetry we experience, the directionality of time, emerges from statistical considerations and the increase of entropy, not from the underlying quantum dynamics. More strikingly, some interpretations of quantum mechanics allow for retrocausality, influence flowing backward in time from future to past. In certain experimental setups called delayed choice experiments, it appears that a choice made in the future can affect the state of a particle in the past. The wave-particle duality of light, for instance, can be controlled by decisions made after the photon has already passed through the apparatus, suggesting that the future measurement retroactively determined what the photon was doing earlier. These effects are real, verified experimentally, though their interpretation remains controversial. Standard quantum mechanics explains them without true backward causation. instead invoking atemporal correlations or the global structure of the wave function. But some physicists take retrocausality seriously as a genuine feature of quantum reality, suggesting that the future and past are more entangled than we typically imagine, that causality might flow in both directions at the quantum level. In dreams, retrocausality feels commonplace. You dream of searching for something before you know what you're searching for. You feel the emotional aftermath of an event before the event occurs in the dream narrative. You recognize a person before they introduce themselves. The dream seems to know where it is going before it gets there, as if the ending reaches back to shape the beginning. This could be explained classically. The brain constructing the dream has access to all the pieces simultaneously and weaves them together in a way that creates apparent retrocausality when recalled linearly. But from a quantum perspective, we might interpret dream time as genuinely non-linear, reflecting the atemporal structure of the quantum wave function. If consciousness is quantum, then the subjective experience of time might not map straightforwardly onto the objective time measured by clocks. The quantum state describes probabilities for different outcomes at different times, but it does not itself unfold in time the way classical states do. The wave function is a timeless object that encodes correlations between past, present, and future. When consciousness is deeply quantum, as it might be during dreaming, the temporal structure of experience could reflect this timeless quality, creating dream narratives where cause and effect are scrambled, where future and past interpenetrate. There is also the phenomenon of time dilation in dreams. A dream that feels like it lasted hours might have occurred in just a few minutes of real time. Or conversely, a brief dream might be packed with so much experience that it feels compressed, as if years passed in moments. These subjective alterations in temporal flow might reflect changes in the quantum dynamics of consciousness, changes in the rate at which wave functions evolve, or the density of quantum events that constitute moments of awareness. Einstein's relativity taught us that time is not absolute, that it dilates and contracts depending on relative motion and gravitational fields. But these effects are tiny in everyday experience, negligible for human speeds and Earth's gravity. In dreams, time distortion is dramatic and commonplace, suggesting that the subjective time of consciousness follows different rules than the objective time of physics. If consciousness is quantum, then perhaps subjective time is quantum time, governed by the evolution of wave functions rather than by the ticking of classical clocks. In waking consciousness, sensory input and attentional rhythms impose a regularity, a tempo that aligns subjective time with objective time. But in sleep, freed from these external constraints, quantum time might run at different rates or in different directions, creating the fluid, non-linear temporality characteristic of dreams. Some dreamers report even stranger temporal experiences. Lucid dreamers who become aware within their dreams sometimes describe being able to control time, to speed it up or slow it down, to rewind events and replay them differently. These abilities, if they are real and not simply false memories constructed upon waking, suggest that conscious control can influence the temporal structure of the dream. That intention can shape the rate and direction of time's flow in the quantum dream space. As you slip further towards sleep, your sense of time is already changing. Minutes stretch. Thoughts drift without clear sequence. The boundaries between now and then begin to blur. In the quantum state you're entering, time might cease to have the linear directional character it possesses during waking. Past and future might coexist, interpenetrate, create loops and paradoxes that feel entirely natural. And when morning comes, when you try to reconstruct the dream as a narrative told in time, you will find that it does not quite fit, that the temporal order was not what it seemed, that in the quantum space of sleep, time itself was superposed. The implications, what quantum dreams mean for reality. If dreams are quantum phenomena, if consciousness itself operates according to the laws of quantum mechanics, then the implications extend far beyond sleep and dreaming. They touch on the deepest questions of philosophy and physics, questions about the nature of reality, the meaning of observation, the relationship between mind and matter, and the fundamental structure of existence. One of the most profound implications concerns the nature of reality itself. In classical physics, the world exists objectively, independently of observation. The moon is there whether or not anyone looks at it. Trees fall in forests and make sounds whether or not anyone hears them. Reality is what it is, regardless of consciousness. But if consciousness is quantum, and if observation plays a fundamental role in collapsing wave functions, then reality might not be independent of consciousness after all. The act of observation might not merely reveal what was already there. It might actually create what is there, selecting one outcome from a spectrum of quantum possibilities. Mind, then, is not a passive receiver of information about an external world. Mind is an active participant in the construction of reality itself. This idea has deep roots in both quantum physics and philosophical idealism. Philosophers like George Berkeley argued centuries ago that existence depends on perception, that to be is to be perceived. Quantum mechanics, with its observer-dependent collapse, seems to give empirical support to such ideas, though the connection remains controversial and contested. If we take the quantum dream hypothesis seriously, then the boundary between dreaming and waking becomes less clear. Both are states of consciousness that construct experiential realities from quantum possibilities. The difference lies in the constraints. Waking consciousness is constrained by sensory input that correlates with the shared external world, ensuring that different observers collapse similar wave functions and experience similar realities. Dream consciousness is unconstrained by such input, allowing private, idiosyncratic collapses that create unique experiential worlds, but neither is more real than the other in an absolute sense. Both are conscious experiences arising from quantum processes. Both involve the collapse of wave functions into definite experiential states. The waking world feels more real because it is shared, because other observers confirm your perceptions, because it is stable and consistent across time. But from the inside, from the perspective of pure experience, the dream can feel equally real, equally vivid, equally meaningful. This perspective dissolves the hard boundary between subjective and objective, between mind and world. If consciousness and matter are both quantum, both described by wave functions that entangle and collapse, then they are not fundamentally different kinds of things. They are aspects of a single quantum reality, different facets of the same underlying process. Mind is not separate from world, observing it from the outside. Mind is woven into world, participating in its actualization, moment by moment. Another profound implication concerns free will and determinism. In classical physics, if you know the initial state of a system and all the forces acting on it, you can predict its future with arbitrary precision. The universe unfolds mechanically, deterministically. Free will, if it exists at all, must somehow emerge from or coexist with this deterministic substrate, and how this is possible remains deeply puzzling. Quantum mechanics introduces indeterminacy. Before measurement, the quantum system is genuinely indefinite, not just unknown. Multiple outcomes are possible, weighted by probability but not determined. The collapse selects one outcome, but which one is selected appears to be fundamentally random, not determined by any prior state or hidden variable. This quantum randomness provides a kind of openness, a loosening of rigid determinism. If consciousness is quantum, and if choices involve quantum processes, then free will might be more than an illusion. The decisions you make might involve genuine quantum indeterminacy, moments where multiple futures are possible, and your choice, your act of observation or intention, collapses the wave function toward one outcome or another. This does not make choice arbitrary or random. It makes it genuinely open, genuinely creative, not predetermined by the past but shaped by consciousness in the moment of decision. In dreams, this quantum freedom might be even more pronounced. The constraints that limit waking choices fall away. In lucid dreams especially, where you're aware that you are dreaming, you can exercise choices that seem impossible in waking life. You can fly, teleport, transform the environment, alter the narrative at will. If these abilities reflect genuine quantum freedom, then dreams might be training grounds for consciousness, spaces where the creative power of quantum choice can be explored and developed without the consequences that attend such choices in the shared waking world. There is also the question of what happens to consciousness when the brain ceases to function. If consciousness is purely a product of classical neural activity, then it ends when the brain dies. But if consciousness is quantum, rooted in processes that transcend individual neurons or even individual brains, then the relationship between consciousness and physical substrates becomes more complex. Some interpretations of quantum consciousness suggest that the quantum aspects of mind might not be entirely dependent on the brain. If consciousness involves quantum entanglements that extend beyond the individual organism, if it participates in a larger quantum field or universal wave function, then physical death might not extinguish consciousness entirely. It might transform it, dissolving the boundaries that the living brain maintains, allowing consciousness to merge back into the quantum substrate from which it emerged. This is highly speculative, bordering on the mystical. There is no empirical evidence for consciousness surviving physical death. No mechanism has been identified that would preserve personal identity or memories after the brain ceases to function. But if we take seriously the idea that consciousness is fundamentally quantum, then we must at least consider the possibility that death is not the absolute end we typically assume it to be, but a transformation. Different kind of wave function collapse that changes the structure of consciousness rather than eliminating it. Dreams in this context might offer a preview of such transformation. Each night you temporarily dissolve the boundaries that define your waking self. You enter a state where identity is fluid, where the usual constraints of embodied existence fall away, where consciousness explores possibilities that waking life does not permit. And each morning you return, reconstituting the coherent self from the quantum flux of sleep. If death is a final sleep, perhaps it involves a similar dissolution, but without the return, without the recollapse into a defined individual identity. These speculations take us far beyond established science. They venture into territory where physics meets metaphysics, where empirical inquiry touches on questions that may ultimately be beyond its reach. But they illustrate the profound implications that follow if we take quantum consciousness seriously, if we accept that mind is not merely an emergent property of complex classical computation, but a fundamental aspect of quantum reality itself. Scientific skepticism and alternative explanations. It is important, even essential, to balance these speculative explorations with rigorous skepticism. The quantum dream hypothesis is not established science. It is a collection of intriguing ideas, suggestive analogies, and provocative possibilities, but it faces serious challenges, both theoretical and empirical. The most fundamental challenge is the decoherence problem. Quantum effects are fragile. They require isolation from environmental noise, protection from thermal fluctuations, and careful control of interactions. In laboratories, quantum computers must be cooled to temperatures near absolute zero and shielded from vibrations and electromagnetic interference to maintain coherence for even brief periods. The brain is the opposite of such an environment. It is warm, wet, noisy, filled with constant molecular motion and chemical reactions. Calculations suggest that quantum superpositions in biological systems, especially in large molecules like proteins, should decohere almost instantaneously, in femtoseconds or picoseconds, far too quickly to play any role in neural processing, which operates on timescales of milliseconds or longer. If microtubules were quantum computers, as Orch OR proposes, they would need to maintain coherence across millions of tubulin proteins for periods long enough to influence neural activity. Most physicists believe this is impossible in the thermal chaos of living cells. Hameroff and Penrose have responded by suggesting biological mechanisms that might protect quantum coherence. They point to the ordered structure of microtubules, which might shield quantum states from environmental decoherence. They note that biological systems have evolved sophisticated mechanisms to manage quantum effects in photosynthesis and other processes, suggesting the evolution could have found ways to harness quantum coherence in neurons as well. But these arguments remain contentious. The quantum effects observed in photosynthesis, while interesting, are very specific and limited. They do not demonstrate that large-scale quantum computation is occurring, or that consciousness depends on such processes. The burden of proof remains on those proposing quantum consciousness to demonstrate experimentally that relevant quantum effects actually occur in the brain, and that they play a causal role in generating conscious experience. Another challenge is the lack of explanatory advantage. Classical neuroscience has made tremendous progress in understanding consciousness without invoking quantum mechanics. Neural networks, synaptic plasticity, oscillatory rhythms, and large-scale brain dynamics provide rich frameworks for explaining cognition, perception, memory, and even aspects of subjective experience. Adding quantum mechanics to this picture adds complexity without, thus far, adding clear explanatory power. Dreams, in particular, can be explained quite well with classical neuroscience. During REM sleep, the brainstem activates the cortex, while the prefrontal regions that handle logical reasoning are less active. This creates vivid imagery and emotional experience without critical evaluation. The random activation of memory circuits produces the fragmented, recombined content of dreams. The subjective experience of time dilation or nonlinear narrative can be explained by the way the waking brain reconstructs the dream upon recall, filling gaps and creating false connections. From this classical perspective, there is no need to invoke quantum superposition, wave function collapse, or entanglement. The brain is doing what brains do, processing information, consolidating memories, exploring hypothetical scenarios. The apparent quantum-like features of dreams, the multiplicity, the non-locality, the temporal strangeness, are simply consequences of how classical neural networks behave when freed from sensory input and executive control. This does not mean the quantum dream hypothesis is wrong, but it does mean that the burden of proof is high. To establish that dreams are genuinely quantum phenomena would require demonstrating quantum effects in the sleeping brain, showing that these effects are necessary for dream generation and ruling out classical explanations. No such demonstration has been made. the hypothesis remains speculative, a provocative possibility rather than a confirmed reality. Moreover, even if quantum effects do occur in the brain, it is not clear that they would have the philosophical implications often attributed to them. Quantum mechanics is strange, but it is also a physical theory, subject to mathematical laws and empirical testing. It does not automatically imply that consciousness is fundamental to reality, or that mind can control matter through quantum collapse. These interpretive leaps go beyond what the physics itself demands. Many physicists and philosophers argue that quantum mechanics has been overinterpreted, that its strangeness has been exploited to support all manner of metaphysical and mystical claims without adequate justification. The measurement problem is real, but it might have solutions that do not involve consciousness at all. Decoherence, spontaneous collapse theories, or the many worlds interpretation all provide ways to understand quantum mechanics without giving observation a special fundamental role. The quantum dream hypothesis should be approached, then, with intellectual humility. It is a beautiful idea, rich in imaginative power and philosophical resonance. It connects ancient questions about the nature of consciousness with cutting-edge physics in provocative ways. But it is not, at this moment, established truth. It is a speculation, a thought experiment, a lens through which to view dreams and consciousness that might illuminate aspects of experience that classical approaches miss, but which remains unproven and perhaps unprovable with current technology. The value of such speculation is not primarily in its truth or falsity, but in its ability to expand our thinking, to challenge our assumptions, to open conceptual space for possibilities we might otherwise dismiss. Whether or not dreams are literally quantum phenomena, thinking about them in quantum terms reveals patterns and puzzles that deserve attention. Questions about the nature of observation, the construction of reality, the relationship between consciousness and the physical world. As you lie here now, on the edge of sleep, it does not matter whether the quantum dream hypothesis is correct. What matters is that you are approaching a state of consciousness different from waking, a state where the rules change, where experience takes forms that waking logic cannot accommodate. Whether this difference is quantum or classical, whether it involves wave functions or merely neural networks, the mystery remains. And it is the mystery itself, not its solution, that invites wonder. Closing. The beauty of quantum uncertainty. We have journeyed tonight through strange conceptual terrain, from the superposition of quantum particles to the superposition of dream narratives, from the collapse of wave functions to the moment of waking, from quantum entanglement to the mysterious connections between memories and experiences. We have explored the possibility that consciousness itself might be a quantum phenomenon, that dreams might offer a window into the deepest structure of reality, that the sleeping mind might access dimensions of existence that waking awareness cannot reach. These ideas are speculative, unproven, perhaps unprovable. They sit at the boundary of science and philosophy, of physics and metaphysics. They challenge our common sense understanding of mind and matter, reality and illusion, self and world. They ask us to consider that the universe might be stranger than we imagine, that consciousness might be more fundamental than we assume, that the line between observer and observed might be more blurred than our everyday experience suggests. But whether or not these ideas are literally true, they point towards something important. They remind us that consciousness remains mysterious, that despite all the progress of neuroscience and physics, we still do not understand how subjective experience arises from physical processes, how it feels like something to be a conscious being, how the private inner world of awareness relates to the public outer world of matter and energy. Dreams in particular resist easy explanation. They're universal yet utterly private, vivid yet ephemeral, meaningful yet illogical. They arise every night from the darkness of sleep, painting worlds that feel real while they last, then dissolving back into darkness when we wake, leaving only fragmentary memories and lingering emotions. They connect us to our depths, to parts of ourselves that waking consciousness seldom acknowledges, to fears and desires, memories and imaginings that shape our lives from beneath the surface of awareness. If dreams are quantum phenomena, then they reveal consciousness at its most fundamental, stripped of the constraints that bind waking perception to consensus reality, exploring the full space of possibilities that the quantum wave function allows. If dreams are not quantum, if they are merely the classical computation of a sleeping brain, they are no less remarkable, no less mysterious, no less worthy of wonder. The beauty of the quantum perspective is not that it provides definitive answers, but that it enriches the questions. It allows us to see dreams not as mere byproducts of neural housekeeping, not as random noise that meaning-seeking minds mistakenly interpret, but as potentially fundamental aspects of consciousness, as explorations of possibility space, as journeys into the deep structure of mind and reality. And it invites us to hold uncertainty lightly, to embrace the fact that we do not know, may never know, whether consciousness is quantum or classical, whether dreams are wave function collapses or neural network activations, whether observation creates reality or merely reveals it. This not knowing is not a failure. It is an opportunity, a space of openness where wonder can flourish, where imagination can play, where the mystery of being conscious can be felt in its full depth. As you drift now into sleep, let these ideas settle like dust motes in sunlight, sparkling and shifting, never quite resolving into clear forms. You need not decide whether dreams are quantum. You need not collapse the wave function of possibility into a definite belief. Instead, simply allow yourself to enter the dream state with a sense of appreciation for its strangeness, its beauty, its resistance to complete understanding. Tonight, you will dream. Neurons will fire in patterns that classical physics can describe, or perhaps quantum states will superpose in microtubules, exploring configuration spaces beyond classical reach. Or perhaps both are true simultaneously, quantum and classical intertwined in ways we have not yet learned to describe. It does not matter which is correct. What matters is that you will experience something extraordinary, something that happens every night yet remains miraculous, the spontaneous creation of entire worlds within the darkness of sleep. Your dreams are wave functions that collapse when you wake up, or they are neural activations that cease when sleep ends, or they are something else entirely, something we have no concepts yet to capture. They are yours and yours alone, private performances in the theatre of consciousness that no other being will ever witness directly, yet they connect you to the universal human experience of dreaming, the nightly dissolution and reconstitution of self that every conscious creature undergoes. In the morning you will wake, and the dream will fade, leaving only traces, fragments, a sense of having been somewhere else, having lived another life, however briefly. The quantum superposition, if it existed, will have collapsed. The many worlds, if they branched, will have separated, leaving you in this branch, this moment, this particular path through possibility. And you will rise and continue your waking life, grounded again in the consensus reality that sensory input and social Agreement maintain. But for now, for these remaining moments before sleep takes you completely, rest in the liminal space, the threshold between waking and dreaming, between classical certainty and quantum possibility. Feel the boundaries dissolving, the constraints loosening, the collapse mechanisms releasing their grip. You're becoming superposed, existing in multiple states at once, beginning to explore the quantum landscape of consciousness. Let your breathing slow and deepen. Let your body grow heavy and still. Let your thoughts drift without direction or purpose. The quantum realm awaits, whether literal or metaphorical, whether physical or purely experiential. It awaits with its strange laws and beautiful paradoxes, its multiple realities and non-local connections, its timeless structures and probability waves. You are the observer and the observed, the wave function and the collapse, the dreamer and the dream. You are Schrödinger's cat, entering the box where multiple states coexist, where you are both here and elsewhere, both one person and many, both conscious and unconscious simultaneously. And in the morning, the box will open, the measurement will occur, and one definite reality will emerge, carrying the memory of tonight's quantum journey encoded in neural patterns or quantum states, preserved somehow in the continuity of self that spans the gap between sleep and waking. But that is morning's concern. For now, there is only the descent, the gentle falling away from definite states into the superposition of dreams. There's only the letting go, the release of the waking world's demands, the permission to exist in multiplicity, in paradox, in the beautiful uncertainty that quantum mechanics teaches us is the fundamental nature of reality itself. Close your eyes, breathe, release, fall gently into the quantum foam of consciousness, where particles and waves, matter and mind, self and world, dissolve into one unified field of possibility. Let the mystery hold you. Let the unknown embrace you. Let sleep and dreams carry you into the heart of existence, where questions dissolve and only direct experience remains. Good night, quantum dreamer. May your wave functions evolve smoothly through the night. May your superpositions explore beautiful configurations. May your collapse, when it comes with morning light, bring you back gently to this definite world, carrying with you some trace of the infinite possibilities you visited in the dark. The universe is stranger than we know, stranger than we can know, stranger perhaps than we can imagine. But tonight, in dreams, you will touch that strangeness directly, live it from the inside, become it for a few precious hours, and that, whether quantum or classical, whether physical or metaphysical, is a miracle worth celebrating. Rest now, dream well, and know that in the morning, when the wave function collapses and you return to waking consensus reality, the quantum realm will still be there, humming beneath the surface of all things, waiting for the next night, the next dream, the next journey into the deep structure of consciousness itself. Sweet dreams, traveller. The quantum mysteries await you.